Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 63 which we are coming up. Again, we are looking into the small signal analysis and modeling of 22 nanometer fully depleted SOI for cryogenic RF CMOS. So in our previous lecture, we had looked into what are the various properties of cryogenic FDSOI CMOS. This time we will be actually doing some modeling of the physical components which are getting affected by cryogenic. Now, what we are trying to now formulate is the whole idea of this lecture is to give you a small signal circuit model which will be able to capture the RF performance of 22 nanometer FDSOI. Why is it important? Because generally when we try to extract the physical parameters of the device, say for example you want to do a transient analysis or you want to do an AC analysis, it is imperative to know the capacitive model and the resistive model, and if there are some inductive component in the model as part of the design, so that you can predict the RC time constant, and therefore you can predict a priori on the first hand principle the values of the various time constants available to you. And this will imply that you will be able to do a sort of a frequency extraction for an RF CMOS at cryogenic temperature. Now, typically, we have already discussed that this model consists of both intrinsic parameters as well as extrinsic parameters. Now, intrinsic parameters are primarily looking, if you look very carefully, the way we define intrinsic and extrinsic is something like this for all our practical purposes. If this is my active area of the device, let us suppose this is the active area, and this is my drain here, right? And this is the drain here, and I have the source here. These are all part of active devices here. Then this part is my intrinsic part, which consists of substrate, inversion layer, and then you have the metal, you have this oxide layer, metal gate. Let's also assume this to be as the part of the intrinsic layer, this whole thing, the one where I have shown the lines here, correct? And what we are looking into is we are also looking into the extrinsic one will be one which is coming from this metal, and this metal, gate metal, and then drain contact. So, source contact, gate contact, and drain contact. Anything beyond this, right, will be defined as the extrinsic parameter. And these have to be accurately extracted in order to understand the value of the transit frequency and the maximum frequency. Now, if you look at the capacitances which are available to you for various capacitances for the device. So, this is basically an FDSOI device which I was talking about. And if you look very carefully on the right hand side, the blue ones which you see, these are all your external capacitances. So, you see this is the internal device itself, and this is the internal parasitic capacitances which you see here, right? So, this is your source here, this is your drain, and this is your gate, right, on the right hand side. So, when I say CGSA, I mean to say a gate to source, and when I say CDSA, I mean to drain to source. So, these are extrinsic parasitic capacitances which are extrinsic to the device itself, right? So, what we say is that we divide the whole thing into two parts, 0.5 on this side and 0.5, so that the total value of gate to source in A part is given by this. Similarly, CDSA, if you take it is 0.5 here and 0.5 here, if you add these two together, I will get drain to source total to be equals to CDSA. Now, the idea here is that these are all extrinsic capacitances and which depend upon the value. If you look now internally within the device structure itself, the lower part of the device, you see you will have 0.5 here, drain to source external extension, and this is gate to source external extension. This is gate to source on the external extension for a double gate device, and this is drain to source for external extension for the double gate device. And this is basically your gate to drain channel which you see. And these are the various distributive capacitances which are available to you between the gate, source, and the drain pad. So, now you have pads like drain pad, you have a gate pad, and you have a source pad, and these right hand side diagrams shows you the parasitic capacitances which are available to these devices at any other temperature. It is not only in cryo, but it is dependent on the whole temperature design, right? This I will come to later on. Let me showcase to you the various numerical values, which these are all extracted experimental values which you get for FDSOI 22 nanometer cryo-CMOS circuitry. And what we get is that if we vary the temperature from 300 up to 70 Kelvin and then 5 Kelvin, how does the various parameters changes that we need to see, right? So if you vary temperature from, this is for an NMOS FDSOI at 18 nanometer NMOS FDSOI, right? This is FDSOI device, and this is at, and these are at 300 Kelvin, then you do at 70 Kelvin, and then you do at 5.5 Kelvin for NMOS, right? And the parameters which we are taking initially are are something like this. We are taking RGE gate, extrinsic gate resistance, gate to source extrinsic resistances, CGD drain, gate to drain extrinsic, and then CDS drain to source extrinsic, right? These are all extrinsic parameters. These are all extrinsic, right? You will also have some intrinsic parameters. Say for example, we can do GMI, which is the transconductance of the intrinsic parameter. We will looking into the GS, gate to source resistance in the intrinsic region, gate to drain resistance in the intrinsic region. We will have CGS, gate to source in the intrinsic region, C, gate to drain in the intrinsic region, and then CDS, drain to source in the intrinsic region. Now let me give you a numerical value which has been extracted. It is taken from the same paper which I had, Chakravarti et al., which I have already mentioned in the previous discussion. RGE is, I am using here, RGE, let me say the value is 338, right? And this is 285, right? And then this is 231, right? Let me come to CGSE. CGSE will be 0.233. This is femtofarad per micrometer. All the capacitances are femtofarad per micrometer, and this is ohms per micrometer. This is ohms per micrometer, the units, right? So this is basically a width quantized resistance in a sense, right? So that you need to find out. This is 0.233 and this is 0.233. And I will tell you what is the interesting case about this one is, as you can see, gate to source extrinsic capacitance is almost independent of the variation in temperature, right? And you can understand why, because it's an extrinsic parameter. And extrinsic parameters are, most of them are basically passive elements as such, which do not show a change in the value of gate to source resistance, and that's the reason it remains like. So most of the extrinsic parameters which you will see, if I plot the value, you will see this is 164. This is again femtofarad per micrometer. This is 0.164. This is also 0.164. If you look at drain to source, again femtofarad per micrometer, the value comes out to be 3.2 into 10 to the power minus 3, 3.2 into 10 to the. So as you can see, my extrinsic parameters are almost independent of the temperature. This is my intrinsic parameter, right? Intrinsic parameter. Let me first come out to be GMI. GMI is basically the transconductance. And interestingly, the transconductance value actually starts to increase at lower temperature, and this is primarily because of the larger threshold voltage model which you developed. Similarly, if you look at RGSI, which is the gate to source intrinsic resistance, this is 0.12, this is 0.9, and then if you go further down, it is 0.075. Look at RGDI, gate to drain intrinsic, will come out to be a 0.8, 0.69, and you get 0.38, right? Then if you look at CGSI, which is gate to source, it is 0.352, 0.355, and this is 0.356, a very minimal increase in the value of gate to source capacitance. This is 1.2 10 to the power minus 4, right? Again 1.2 10 to the power minus 4, 1.2 into 10 to the power minus 4. Similarly, if you look at this point, the same values are applicable for drain to source resistances. This is quite interesting phenomenon. If you look very carefully, most of the parameters changes just from 70 to 5.5 variation. When you see a change. For otherwise, it don't see a change, and that is primarily most of the parameters show a change because of the change in the value of the mobility which is taking place at such a low temperature, and that makes it this functionality of an 18 nanometer FDSOI more so a much better sort of design parameter. Now, if we come to the point where you do a benchmarking, so I will do a benchmarking and we will try to compare the figure of merit of the this work with that of the present current work. So, if you take for example, if you take gate length as one of the parameters, VDD as another parameter, a subthreshold slope between N and P, right, at 77K, then this is again NPGM. This is GM in the linear region and this is GM in the saturated region. Again N by P, and this is N by P of transit frequency and N by P of F max. Then if you plot write the whole idea, then various research papers have committed that if it is 30 nanometer, then it comes out to be 0.8 volts which we use. This is 30 by 36. Now you see, quite interestingly, your subthreshold slope at 77K is much smaller as compared to 300 Kelvin, which we have already seen here, which means the switching speeds will be much larger in this case. If you look at the transconductance, it is approximately plus 37 to plus 35% change which is happening in the transconductance for linear region, and for this it is plus 19 to 20% change which will happen. FT and Fmax is not available. Similarly, if you look at the work presented by this paper, it is basically a 22 nanometer FDSOI, and therefore its channel length is taken to be 18 nanometers here. And if you compare this with this thing, we use VDD of 1.0 volts, and then this is 26 by 28. This is plus 60 and plus 71 percentage, which you get. This is plus 38 and plus 27 percentage, and then you get this to be as 495 337, which I have already told you at 5.5 Kelvin earlier, and this happens to be 497 372 at 5.5 Kelvin. So you see, what we have gained from all this discussion is that typically when you actually do FDSOI technology at 22 and try to compare with the state of the art, the value of the FTF max are relatively much larger in this case, right? And that is because of the fact that your GM has been relatively larger when you go for low values of temperature. So two things as a cryogenic engineer you need to find out is how the parameters are changing. Major change in the parameter which affects the value of FTF max is basically your GM, transconductance, and of course the mobility and the current flowing through the device itself. Now with this understanding, let me now again go back to a detailed understanding of at least the FDSOI device cross section with various parasitics which you see. So FDSOI is, this is the box layer which you see on the right hand side, right? And you have the source here and drain here, and this includes both intrinsic and extrinsic parameters. So these all are the red colored ones which you see here are all intrinsic. This is all intrinsic in nature, intrinsic, and these are all extrinsic, right, which is going outside the pad as well as still from the drain upwards is all your extrinsic layer which you see. M1 is the first metal layer. The first metal layer is M1, and it is basically connected to the gate and source and the drain. So when we say M1, it is basically the gate which is connecting the three layers so source, metal gate and drain, right? Now, and this serves as a RF reference plane, initial RF reference planes. And this circuit takes care of almost all the parasitics and resistances, which is consisting of interconnects as well as device terminal. So let's go one by one. The intrinsic parameters are given as GMIT, which is the intrinsic transconductance, right? We have an output conductance, and we have CGSI, gate to source intrinsic, gate to drain, and source to drain intrinsic capacitances. And let's start for the red one first, right? So that red one is, this one is RSE. This is the source extension resistance. So what is happening is the source has got a doping concentration, right? Its resistance is though relatively small, but there will be nonetheless a drop of voltage across source and drain, and that is taken care of by RSE here and RDE on this side, right? So these are the two resistance which is there within the drain and source layer itself, right? Then you will also have, as you go further inside, RGSI and RGDI. This is basically gate to source intrinsic resistance, and this is gate to drain intrinsic resistances. So gate to source and gate to drain intrinsic resistance, which you will see. And therefore, this R0 is basically the resistance, channel resistance, which you see, small signal channel resistance. Obviously, when the current is flowing, and you all know that the channel will start behaving like a VVR, a voltage variable resistor. And what will happen? This R0 will be a function of some value. Now, this GMI is the intrinsic transconductance, and therefore, what I am trying to tell you is that when the device is in saturated state, the inversion layer is basically looking like current source with two resistances CGDI and CGSI carried to the edge. Now, let's look at the extrinsic part here, which is going from away from the source, and this is the extrinsic part. This is CDE, gate to drain extension, and this is your drain to source extension, extrinsic one, and this is your gate to source extrinsic one. So this, because you will have always an overlap of the gate with the source, right, and therefore that will be an overlap. Capacitance will always be available. I am not assuming any self-aligned structure for sure. Then you will always have the gate to drain intrinsic one. Gate to drain intrinsic one will be internal to the capacitances, and there will be two of them, which is basically this and this. So this takes care of most of the element within the device itself. Let's now go to the outside the device. So this is your D. So this is A. There are two devices, and this is RSA and RDA is basically the resistances in the contact for our drain and source. Of course, this, when you go till the metal layer, from the source to the metal layer, there is an inductive channel also available to you, which is LDA and LSA, the source side and the drain side. These are inductive elements which are available. And why we give it is, when you do a non-quasi-static modeling, we need to ensure that the current is sort of delayed by certain amount because of the reasons already discussed with you, and that is emulated upon by this inductor. If you go further to the top, away from the metal one gate and right into the domain, extrinsic domain, then you will have two capacitances added together, CGD, gate to drain of A, plus CDE extension, external extension region. You add, these two are in parallel, and if you add them, you get this like. Then the same thing happens here, and the same thing happens, the gate to source and gate to source extension region, right. This is the gate to source extension, gate to source, this one. This is gate to drain, right, and this is drain to source and drain to store extension region. So these are the few elements of the device which needs to be looked into while designing the parasitics of the device. Okay, so let's look at we have understood this, and we will replicate the same thing here. Sorry, we will replicate the same thing here at this particular point, and this is just exactly the same representation of the previous diagram, but in a much more linear scale. And what we see here is that extrinsic one is the red colored one, right. The red colored ones are all extrinsic in nature, the blue ones are all intrinsic in nature. So what we have seen is that you will have always a GMI, which is the intrinsic capacitances, and these might be in the linear region or saturation region. There will be also G0, which is basically output conductance. Output conductance is given as del ID, del VDS, right. This is output conductance which you get. This is your R0, and 1 upon this will be your conductance G0. So this will be G0. GM will be equals to del ID del VGS, right, and that's how you get the value of GM and CGS. As you can see, CDSI and CGSI are parallel to each other. However, on the gate side, you have an extra resistance known as gate to source resistance, which is there, and this accounts for the overlap resistance which happens. Similarly, you have gate to drain here and gate to drain resistances and capacitances here. The red colored ones are basically the intrinsic elements which you see. Of course, as I discussed with you, these are all the inductive elements which takes care of the delay within the cell itself, and that gives me a good idea about what the small signal equivalent circuit diagram of the device is concerned. Now, same thing I'm just repeating here, the G0 is the output conductance, GM INT is basically your intrinsic transconductance. Please understand GMIT INT, which is the intrinsic transconductance, is actually a function of the gate voltage. So when your gate voltage varies, And similarly, it's also a function of drain voltage. When they vary, your GMINT will also go on varying. So you need, as a designer, if you want the maximum gain out of the FDSOI structure, we need to fix up a point of bias where GMINT is the largest in nature. The extrinsic blocks will include RGE, which is gate intrinsic, source intrinsic, drain intrinsic, and CGS, CGD we have already discussed at the extrinsic parameter. So now what we do as a designer is we take up individual elements, passive elements and active elements, and check out how these values will go on varying with respect to temperature. From once we know that, we can extract the various RF figure of merits for cryogenic conditions. Now let me do an S parameter modeling here. So we will do an S parameter analysis. The S parameter are known as scattering parameter, and they are generally used to describe the RF behavior of MOSFET in both terms of reflection coefficient and transmission coefficient. Now, the small signal equivalent circuit model is generally used to extract the intrinsic and extrinsic transistor parameters from the measured S value. So what you do is that you measure the S value, scattering matrix parameter value, and from there you get the values of intrinsic and extrinsic transistor parameters. We assume that the access transistors and inductances are temperature invariant. They are almost constant with respect to temperature. Now, interconnect line decreases, the resistance of the interconnect line decreases at cryogenic temperature, right? But due to its very small magnitude of the order of even less than 3 ohms to 5 ohms, they generally don't put much or influence much at cryogenic temperature. The various key extracted parameters which generally the designer follows is basically an intrinsic transconductance parameter. We look after source drain resistance, gate capacitances, gate resistances, and output conductance. You need to also ensure that these parameters, the variation of these parameters with respect to temperature, we need to find out analytically as well in order to appreciate how these key extracted parameters change with temperature. The reason being that for example, I'll give you a small example that as you lower your temperature, the intrinsic transconductance changes, right? Similarly, your resistance passive elements, though they don't change too much, but nonetheless, if you're talking in terms of microampere, there will be a small change in the value of the source and drain resistances, right? And it has to do with how you see the trapping and detrapping of charges within the network. At very low temperature, you don't allow the trapping and detrapping to happen very often as you would have allowed at 300 Kelvin, and that varies the value of the resistance here. The output conductance also varies with respect to the amount of current which is flowing for a fixed bias of VGS and varying values of VDS. Let's look S parameter Smith chart here, and these are the figure here actually shows the measured as well as model S parameter for 3 temperature ranges: 300 Kelvin, 70 Kelvin, and 5.5 Kelvin. The line ones are basically your small signal equivalent model, and the symbols which you see, the rounded signals, are basically the experimental part. So as you can see here, they are matching very well. The Smith charts are matching very well for the various modes of parameters which is available: S11, S12, and so on and so forth. And then, so as you can see here, at 300 Kelvin, there's a good agreement between experimental and model parameters for all values of S across all S parameters, the 4 S parameters which are available. At 70 Kelvin, the agreement is very well maintained, and also at 5.5 Kelvin, which means that the model which have been proposed by these authors matches very well with the experimental data when they have designed these devices for the purpose of cryogenic operations. Now let us go to the extracted small signal model parameter trends. What we have seen is, and what the experiment have shown is that the intrinsic transconductance improves by approximately 39% for NMOS and approximately 28% for PMOS at low temperatures, And this is primarily because of reduced phonon scattering, because your temperatures have fallen so low that your phonon scattering limited mobilities have actually become much higher. Now, below 150 Kelvin, the improvement is not that much, but due to the surface roughness scattering, because that will remain so, right? The surface roughness scattering will remain so, and it starts to show its effect beyond below 150 Kelvin. Source drain resistance, which is RGSC and RDE, is basically reduced by about 11 to 12% at cryogenic temperature. And this is primarily because of lower sheet resistivity saturating below 100 Kelvin. So, below 100 Kelvin, the sheet resistance remains almost saturated independent of the temperature. And that's the reason you will see that RGSC and RDE will actually fall down by approximately 11 to 12%. Gate capacitances CGGI and CGGE, which you have done. CGGI, which is the intrinsic part, right? This scales with the gate length, obviously, because as you scale the gate lengths, the amount of, so if you know capacitance is epsilon naught T, A by T oxide. So when you change the gate length dimensions, your WL changes. So W into L, the area changes, and therefore it scales down my CGGI in a much more linear fashion. Whereas when you talk of extrinsic capacitances, there is no such change happening with change in the gate length at least, right? And therefore it remains almost constant independent of the structural parameter which is available to us. So what we have found out is that typically your improvement in the intrinsic transconductance takes place by 39% for NMOS and 28% for PMOS. As you can see, NMOS improvement is much better as compared to PMOS, and that is expected also because of the higher mobility of NMOS. Source drain resistance shows a minor improvement, and the gate capacitance also shows, it tells you that it is almost invariant of the various values. Now, output conductance increases at low temperature, and this is because of reduced short channel effects and due to partial dopant deactivation, right? At very low temperature, there is what is known as a partial dopant deactivation. The dopant species are not able to contribute to the total current by providing an excess charge carrier to the system, and that's the reason it is defined as a partial dopant deactivation. When we discuss about design, we say that it is almost incomplete ionization which has happened. And therefore, these combined effects which we talked about in the previous slide and this slide actually observes improvement in the value of Ft and Fmax at cryogenic temperature. So let me recapitulate what we did in this half an hour. Is we looked into the various models available to us, small signal model of an FDSOI. There we didn't talk about temperature, but we came to know that if you have the FDSOI structure available, I can predict a priori what will be the value of FDF max by knowing the total capacitances and resistance which are offered in the intrinsic as well as in the extrinsic region of the FDSOI. Okay, let me conclude the talk with the basic recapitulation of what we have done today. We looked into the various small signal models available for the FDSOI 22 nanometer, and we also saw that if you reduce the temperature, what are the various electrical and structural parameter changes with temperature. In our next discussion, we will be now going into a new structure, which is a nanosheet structure, and there we will be looking into the structural as well as the electrical parameter variation with respect to temperature. So first we will discuss about 300 Kelvin, and then we will go for lower temperature, which is approximately 4.5 to 5.5 Kelvin. I hope you enjoyed the lecture. Thank you very much.